Did it really happen? What if everything you were ever taught about how the universe began was only half the story? What if the most powerful telescope ever built by human hands just found something so shocking, so unexpected, so fundamentally reality-altering that it forced scientists around the world to sit down, take a deep breath, and reconsider everything they thought they knew about the origin of all existence? What if I told you that right now, as you are watching this, there is growing scientific evidence? Not science fiction, not speculation, not clickbait, but real, peer-reviewed, mathematically rigorous scientific evidence suggesting that the Big Bang, the single most important event in the history of everything, might not have been alone? That there might have been a second Big Bang, a hidden explosion, a shadow creation event that happened shortly after the one we all know about, and that this second Big Bang created something so mysterious, so invisible, so fundamentally different from everything you and I are made of, that we have never been able to see it, touch it, measure it, or detect it directly, despite the fact that it makes up 85% of all the matter in the entire universe. 85%. Think about that for a moment. Everything you can see, every star in the night sky, every galaxy spinning in the cosmic void, every planet orbiting every sun, every mountain, every ocean, every tree, every cell in your body, every atom and every molecule and every grain of sand on every beach on Earth, all of that, all of it combined, represents just 15% of the matter in the universe. The other 85% is invisible. It is dark matter. And according to a radical new theory that is gaining serious traction in the physics community, this dark matter was not created in the Big Bang we all learned about in school. It was created in a completely separate explosion. A dark Big Bang. And the James Webb Space Telescope, humanity's most extraordinary instrument for peering into the depths of time and space, has found clues, tantalizing, mind-bending, impossible-to-ignore clues, that this might actually be true. Now, before we go any further, I want you to understand something about this video. This is not going to be a surface-level overview. This is not going to be a 5-minute summary where I wave my hands and say, "Scientists found something cool," and move on. No. Today, we are going deep. We are going to the very foundation of reality itself. We are going to trace the entire history of the universe from its first fraction of a second to the present day. We are going to understand what the Big Bang actually was, not the cartoon version, not the oversimplified textbook version, but the real, detailed, step-by-step scientific account of how everything came into existence. We are going to explore the James Webb Space Telescope, what it is, why it cost $10 billion, how it works, and what it was designed to find. Then we are going to confront the crisis, because James Webb found things it was never supposed to find. Galaxies that are too big, too bright, too structured, too mature. Galaxies that, according to everything we thought we knew, simply should not exist. And these impossible galaxies have sent shockwaves through the scientific community, forcing physicists to consider ideas that would have been dismissed as fantasy just a few years ago. We are going to explore those ideas. Monster stars thousands of times more massive than our sun, dark stars powered not by nuclear fusion, but by the annihilation of dark matter, mysterious little red dots that turned out to be something nobody expected, and the earliest supernova ever detected. A star that exploded when the universe was just 730 million years old. And then, armed with all of that knowledge, we are going to tackle the central question of this video head-on, the dark Big Bang theory. What it is, who proposed it, why it makes sense, what evidence supports it, what evidence challenges it, and how, within our lifetimes, we might be able to prove whether or not it actually happened. And finally, We are going to zoom out and ask the biggest questions of all. What does this mean? What does it mean for our understanding of reality? What does it mean for our place in the universe? And what does it mean for the future of human knowledge? This is going to be one of the deepest, most comprehensive explorations of the universe's origin you have ever experienced. So settle in, get comfortable, because we are about to take a journey that stretches from the very first instant of time to the cutting edge of human discovery. And if you are the kind of person who loves this, who loves going deep, who loves understanding the universe not at a surface level but at its core, then this channel was built for you. Before we dive in, take 1 second and hit that subscribe button. Turn on the notification bell, because this is what we do here. We explore the biggest questions in the universe with the depth and curiosity they deserve. And drop a comment right now. I want to know what you think before we even start. Do you believe the Big Bang was the only beginning? Or do you have a feeling, a suspicion, an intuition that there might have been more? Tell me. I read every single comment. Let us begin. To understand why the idea of a second Big Bang is so revolutionary, you first need to truly understand the first one. And I mean truly understand it. Not the simplified version. Not the version where someone says there was an explosion and everything flew outward. That version is not just oversimplified. It is actually misleading in several important ways. The Big Bang was not an explosion in space. It was an explosion of space itself. There was no pre-existing void that the universe expanded into. There was no empty room waiting to be filled. Space itself, and time itself, came into existence with the Big Bang. Before that moment, and I need to be careful with the word before, because it might not even be meaningful, before that moment there was no space, there was no time, there was no matter, there was no energy, there was no thing at all. And if you find that hard to wrap your mind around, you are in excellent company, because it is one of the most profound and disorienting concepts in all of science. The question, what came before the Big Bang, might be like asking, what is north of the North Pole? It is a question that sounds perfectly sensible, but may not have an answer because the framework in which the question makes sense breaks down at that boundary. So let us start from the very beginning, the very, very beginning. And when I say beginning, I mean a timescale so unimaginably small that no human metaphor can truly capture it. We are talking about the Planck epoch, which spans from time 0 to approximately 10 to the negative 43 seconds after the Big Bang. That is a decimal point followed by 42 zeros and then a 1. This is the smallest meaningful interval of time that physics can describe. It is called the Planck time, named after Max Planck, the father of quantum mechanics. And during this incomprehensibly brief instant, the entire universe, everything that would eventually become every galaxy, every star, every planet, every living thing, was compressed into a region smaller than a proton. Not the size of an atom, not the size of a nucleus. Smaller than a proton. The temperature was approximately 10 to the 32 Kelvin. That is a 1 followed by 32 zeros in degrees Kelvin. For comparison, the center of the Sun is about 15 million Kelvin. The center of the most massive star in the known universe is maybe a few billion Kelvin. 10 to the 32 Kelvin is a temperature so extreme that the very concept of temperature, as we normally understand it, begins to lose meaning. And at this temperature and density, something extraordinary was happening. All 4 fundamental forces of nature were unified into a single force. Now, to understand why that is significant, you need to know what the 4 fundamental forces are, because they are the architects of everything. The first is gravity, the force that keeps your feet on the ground, the Earth in orbit around the Sun, and galaxies from flying apart. The second is electromagnetism, the force responsible for light, electricity, magnetism, chemical bonding, and essentially all the phenomena of everyday life beyond gravity. The third is the strong nuclear force, the force that holds protons and neutrons together inside atomic nuclei and holds quarks together inside protons and neutrons. It is the strongest force in nature, but it operates only at extremely short ranges, on the scale of atomic nuclei. The fourth is the weak nuclear force, the force responsible for certain types of radioactive decay and nuclear reactions, including the reactions that power the sun. In the universe today, these four forces are completely separate. They behave differently, they operate at different scales, they are described by different mathematical frameworks. But during the Planck epoch, they were all one. They were unified into a single superforce, and we currently have no scientific theory that can fully describe this unification. Our best theory of gravity, Einstein's general relativity, breaks down at these extreme conditions. Our best theory of the other three forces, quantum field theory, also cannot handle this regime. The theory that would describe this, a quantum theory of gravity, is the holy grail of theoretical physics, and it does not yet exist. String theory is one candidate. Loop quantum gravity is another, but neither has been confirmed. So the Planck epoch remains, in a very real sense, the edge of human knowledge, the boundary beyond which we cannot see, even with our most powerful mathematical tools. After the Planck epoch, we enter the grand unification epoch, which spans from about 10 to the negative 43 seconds to 10 to the negative 36 seconds after the Big Bang. During this phase, gravity has separated from the other three forces and is now behaving as an independent force. But the strong nuclear force, the weak nuclear force, and electromagnetism are still unified into a single force, described by what physicists call a grand unified theory, or GUT. The temperature has dropped, but dropped is relative. It is still around 10 to the 28 Kelvin, unimaginably hot. The universe is still incredibly small, incredibly dense, and filled with a seething plasma of exotic particles and antiparticles popping in and out of existence. There are no atoms. There are no protons or neutrons. There are not even quarks in the way we normally think of them. Everything is in a state of primal chaos, governed by physics we are only beginning to understand. And then something pivotal happens. At around 10 to the negative 36 seconds after the Big Bang, the strong nuclear force separates from the electroweak force. This symmetry breaking releases an enormous amount of energy, and this energy triggers one of the most important events in the history of the universe: cosmic inflation. Inflation is a period of exponential expansion. Not just fast expansion, exponential expansion. During inflation, the universe doubled in size not once, not twice, but at least 60 times in a span of about 10 to the negative 32 seconds. To put this in perspective, imagine taking a single proton and inflating it to the size of the observable universe. That is roughly what happened during inflation. A region of space smaller than an atom expanded to the size of a grapefruit, or possibly much, much larger, in a time interval so short that light would not have had time to cross a single proton. This is not expansion at the speed of light. This is expansion far, far faster than the speed of light. And before you object and say, "Wait, nothing can travel faster than light," you are right. Nothing can move through space faster than light. But space itself can expand at any rate. There is no speed limit on the expansion of space. And during inflation, space expanded at a rate that defies all normal intuition. Why does inflation matter? It matters because it solves several deep problems in cosmology. First, It explains the horizon problem, why the universe looks the same in every direction, even in regions that are too far apart to have ever been in contact with each other. Before inflation, these regions were close enough to exchange energy and reach the same temperature. Inflation then stretched them apart to vast distances. Second, inflation explains the flatness problem, why the geometry of the universe appears to be perfectly flat rather than curved. Inflation stretches any initial curvature to flatness, just as inflating a balloon makes its surface appear flat if you zoom in enough. And third, inflation explains the origin of all structure in the universe. During inflation, tiny quantum fluctuations, random, unavoidable jitters in the quantum fields, were stretched to macroscopic scales. These fluctuations became the seeds of all cosmic structure, the tiny density variations that eventually grew, under the influence of gravity, into galaxies, galaxy clusters, and the vast cosmic web we see today. Without inflation, we cannot explain why the universe looks the way it does. With inflation, everything falls into place. After inflation ends, the universe enters a phase called reheating. During inflation, the energy of the universe was stored in the inflaton field, the quantum field that drove the exponential expansion. When inflation ends, this field decays, and its energy is converted into a hot, dense plasma of particles. This is, in a sense, the moment when the matter and radiation of the universe are truly created. The universe is now filled with quarks, antiquarks, gluons, leptons, photons, and all the other fundamental particles of the standard model of particle physics. The temperature is extremely high, around 10 to the 27 Kelvin, but the universe is now expanding at a more sedate rate, governed by the normal equations of general relativity. We then enter the quark epoch, from about 10 to the negative 12 seconds to 10 to the negative 6 seconds after the Big Bang. During this period, the universe is a quark-gluon plasma, a state of matter where quarks and gluons are not bound together into protons and neutrons, but are free to move independently. This is an exotic state that we have only recently been able to recreate in particle accelerators like the Large Hadron Collider at CERN, by smashing heavy nuclei together at nearly the speed of light. In the early universe, this was the normal state of matter. Everything was a hot, seething soup of free quarks and gluons, interacting constantly via the strong nuclear force. As the universe cools further, we enter the Hadron epoch, which begins at about 1 microsecond after the Big Bang and lasts until about 1 second after. During this epoch, the temperature drops enough for quarks to become confined inside hadrons, particles made of quarks bound together by the strong force. The most familiar hadrons are protons, 2 up quarks and 1 down quark, and neutrons, 2 down quarks and 1 up quark. At the same time, matter and antimatter are annihilating each other. For every billion pairs of quarks and antiquarks that annihilate, 1 extra quark remains. This tiny asymmetry, 1 part in a billion, is the reason the universe contains matter at all. Without this asymmetry, all matter and antimatter would have annihilated completely, leaving a universe of pure radiation with no atoms, no stars, no planets, and no life. Why there was this slight excess of matter over antimatter is one of the great unsolved mysteries of physics, known as baryogenesis. We do not know the answer, but we owe our existence to it. Next comes the lepton epoch, from about 1 second to about 10 seconds after the Big Bang. During this period, leptons, electrons, muons, taus, and their corresponding neutrinos dominate the energy density of the universe. Neutrinos decouple from the rest of matter during this epoch, meaning they stop interacting and begin streaming freely through the universe. These cosmic neutrinos are still out there today, forming a cosmic neutrino background, the neutrino equivalent of the cosmic microwave background, though we have not yet been able to detect them directly because neutrinos interact so weakly with matter. And then, between about 10 seconds and 20 minutes after the Big Bang, something truly remarkable happens: Big Bang nucleosynthesis. This is the process by which the first atomic nuclei are forged. The universe has cooled enough for protons and neutrons to begin fusing together, forming the nuclei of the lightest elements. The process creates hydrogen, which is just a single proton, deuterium, 1 proton and 1 neutron, helium, 3, 2 protons and 1 neutron, helium, 4, 2 protons and 2 neutrons, and trace amounts of lithium, 7. And that is it. Nothing heavier. The universe is expanding and cooling too quickly for heavier elements to form through fusion at this stage. The result is a universe that is approximately 75% hydrogen and 25% helium by mass, with tiny trace amounts of deuterium and lithium. And here is the crucial point. This prediction, these specific abundances, is one of the 3 pillars of evidence for the Big Bang theory. When we measure the actual abundances of light elements in the most pristine, unprocessed regions of the universe, they match the predictions of Big Bang nucleosynthesis with remarkable precision. No other theory explains this. No alternative model for the origin of the universe comes close to reproducing these numbers. This is not a vague, hand-wavy confirmation. It is a precise, quantitative match between theory and observation, and it gives us enormous confidence that the Big Bang framework is fundamentally correct. After nucleosynthesis, the universe enters the photon epoch, which lasts from about 3 minutes to approximately 380,000 years after the Big Bang. During this entire period, the universe is filled with a hot, opaque plasma of protons, electrons, and photons. The photons, particles of light, cannot travel freely because they keep bouncing off the free electrons. The universe is like a thick fog. Light is trapped, scattered, absorbed, and re-emitted constantly. You could not see anything. The universe was glowing, but it was opaque. And this state persists for hundreds of thousands of years as the universe slowly cools. And then, at approximately 380,000 years after the Big Bang, something extraordinary happens. The temperature drops to about 3,000 Kelvin, roughly the temperature of the surface of a cool red star, and at this temperature the free electrons are finally captured by the protons to form neutral hydrogen atoms. This process is called recombination, a somewhat misleading name since the electrons and protons had never been combined before. They are combining for the first time. With the free electrons now bound inside atoms, photons are no longer being scattered. For the first time in the history of the universe, light can travel freely. The universe becomes transparent. And the light that is released at this moment, the photons that were finally set free, has been traveling through the universe ever since. For 13.8 billion years, this light has been streaming through space, cooling and stretching as the universe expanded. Today, we detect it as a faint glow of microwave radiation coming from every direction in the sky. This is the cosmic microwave background, or CMB, and it is the second great pillar of evidence for the Big Bang. The CMB was discovered accidentally in 1965 by Arno Penzias and Robert Wilson, 2 radio astronomers working at Bell Telephone Laboratories in Holmdel, New Jersey. They were testing a new ultra-sensitive microwave antenna and kept picking up a persistent, unexplained noise. It came from everywhere. It did not matter which direction they pointed the antenna. The noise was always there, constant and uniform. They initially thought it was a malfunction. They even thought it might be caused by pigeon droppings inside the antenna. They actually found pigeons nesting there and cleaned it out, but the noise persisted. Eventually, they contacted Robert Dicke and his colleagues at nearby Princeton University, who had been independently predicting that such a background radiation should exist as a relic of the Big Bang. Penzias and Wilson had stumbled upon one of the most important discoveries in the history of science. They received the Nobel Prize in Physics for it in 1978. The CMB has a temperature of 2.725 Kelvin, just a few degrees above absolute zero. It is a nearly perfect blackbody spectrum, which is exactly what the Big Bang theory predicts. And when we map it in exquisite detail, as the COBE, WMAP, and Planck satellites have done, we find that it is extraordinarily uniform. The same temperature in every direction to within 1 part in 100,000. But those tiny variations, those minuscule fluctuations of a few millionths of a degree, are the seeds from which all structure in the universe grew. They are the fingerprints of quantum fluctuations from the inflationary epoch stretched to cosmic scales. They are, in a very literal sense, the blueprint of everything. Every galaxy, every star, every planet, every person, all of it grew from those tiny ripples in the CMB. The third pillar of evidence for the Big Bang is the expansion of the universe itself. In 1929, Edwin Hubble made one of the most revolutionary observations in the history of astronomy. By studying the light from distant galaxies, he discovered that nearly all of them were moving away from us, and that the farther away a galaxy was, the faster it was receding. This relationship, velocity proportional to distance, is known as Hubble's law. It was the first observational evidence that the universe is expanding, and if you run the movie backwards, if you imagine reversing the expansion, everything converges to a single point. The universe was smaller in the past, denser in the past, hotter in the past. Go back far enough, and you reach a state of infinite density and temperature, the initial singularity. The Big Bang. Hubble's discovery, combined with Einstein's general relativity, which had predicted a dynamic universe years earlier, though Einstein himself had initially resisted the idea, established the expanding universe as a cornerstone of modern cosmology, and subsequent observations have confirmed and refined this picture enormously. We now know that the expansion of the universe is not just continuing, it is accelerating. The galaxies are not just moving apart, they are moving apart faster and faster. This acceleration was discovered in 1998 by two independent teams studying distant Type 1a supernovae, and it earned Saul Perlmutter, Brian Schmidt, and Adam Rees the Nobel Prize in 2011. The cause of this acceleration is attributed to dark energy, a mysterious form of energy that permeates all of space and drives it apart. Dark energy makes up about 68% of the total energy content of the universe. Combined with dark matter at 27%, this means that ordinary matter, everything we can see and touch, accounts for just 5% of the universe. We are a tiny minority in a cosmos dominated by things we do not understand. Now, after recombination and the release of the CMB, the universe enters a period known as the Cosmic Dark Ages. This is a time of profound quiet. There are no stars. There are no galaxies. The universe is filled with neutral hydrogen and helium gas, slowly cooling, slowly expanding. Gravity is working, pulling the slightly denser regions of gas together, building the scaffolding of what will eventually become the cosmic web, the vast network of filaments and voids that defines the large-scale structure of the universe. But there is no light. The universe is dark, and this darkness persists for roughly 100 to 200 million years. It is a cosmic intermission, a pause between the dramatic birth of the universe and the equally dramatic ignition of the first stars. And it is during this dark age, and the period immediately after, that the James Webb Space Telescope was specifically designed to observe. Because what happens next, the cosmic dawn, the birth of the first stars and galaxies, is one of the most important and least understood chapters in the history of the universe. The first stars, known as population 3 stars, are believed to have formed somewhere between 100 and 200 million years after the Big Bang. They formed from primordial gas, hydrogen and helium, with no heavier elements at all, because heavier elements had not yet been created. And because of their composition, these first stars would have been radically different from the stars we see today. Without heavier elements, which astronomers confusingly call metals, regardless of whether they are actually metallic, the primordial gas could not cool as efficiently. Today, heavier elements in gas clouds radiate energy away, allowing the gas to cool, collapse, and fragment into smaller clumps that form individual stars. But in the primordial universe, without these coolants, gas clouds collapsed more slowly and fragmented less, leading to the formation of much more massive stars. Population 3 stars are predicted to have been enormous, perhaps 100, 1,000, or even 10,000 times the mass of our Sun. They would have burned incredibly hot, with surface temperatures of 100,000 Kelvin or more, compared to our Sun's 6,000 Kelvin, and incredibly bright. And they would have lived fast and died young. A star with 100 solar masses might live for only 2 to 3 million years, compared to our Sun's 10 billion year lifespan. When these population 3 stars died, they died spectacularly. The most massive ones would have exploded as supernovae of unprecedented power, called pair instability supernovae, scattering their nuclear fusion products into the surrounding gas. And those fusion products included heavier elements: carbon, oxygen, nitrogen, silicon, iron. These elements, seeded into the interstellar medium by the deaths of the first stars, became the raw materials for the next generation of stars, population 2 stars, and eventually for planets, and eventually for life. Every carbon atom in your body, every iron atom in your blood, every calcium atom in your bones, was forged inside a star that lived and died before our Sun was born. You are, quite literally, made of stardust. And the very first of those stardust factories were the population 3 stars that ignited at the end of the cosmic dark ages. When these first stars turned on, they did something else that was profoundly important. They ionized the universe. Their intense ultraviolet radiation stripped electrons from the neutral hydrogen atoms surrounding them, creating expanding bubbles of ionized gas. As more and more stars formed, these bubbles grew and merged until, eventually, the entire universe was ionized again. This process is called the epoch of ionization, and it is believed to have been largely complete by about 1 billion years after the Big Bang. The epoch of ionization is one of the key science targets of the James Webb Space Telescope, because it represents the transition from the simple, dark universe of the Dark Ages to the complex, luminous universe of galaxies and stars that we see today. Understanding how and when ionization happened, and what sources drove it, is essential to understanding how the universe as we know it came to be. Now that you have a solid foundation of what the Big Bang was, and what happened in the first billion years of the universe, it is time to talk about the instrument that has changed everything: the James Webb Space Telescope. And to understand why JWST is so revolutionary, you need to understand the limitations of what came before it. The Hubble Space Telescope, launched in 1990, was one of the most successful scientific instruments in history. It observed invisible and ultraviolet light, with some capability in the near-infrared. It gave us the Hubble Deep Field, the Ultra Deep Field, and the Extreme Deep Field. images of thousands of galaxies stretching back billions of years. Hubble discovered that the expansion of the universe is accelerating. It helped determine the age of the universe. It found evidence for supermassive black holes at the centers of galaxies. It captured breathtaking images of nebulae, star-forming regions, and planetary systems. Hubble transformed our understanding of the cosmos. But Hubble had limits, and those limits became increasingly apparent as astronomers tried to push deeper and deeper into the early universe. The fundamental problem is this: the earliest, most distant objects in the universe have their light redshifted. As the universe expands, it stretches the wavelength of light traveling through it. Light that was emitted as ultraviolet or visible light billions of years ago has been stretched, by the time it reaches us, into infrared wavelengths. The more distant the object, the more its light is redshifted, and the deeper into the infrared it falls. Hubble could see some near-infrared light, but it was not optimized for it. To truly observe the first galaxies, the first stars, and the end of the Dark Ages, we needed a telescope specifically designed for infrared observation. A telescope far larger, far more sensitive, and far colder than Hubble. We needed the James Webb Space Telescope. JWST was the product of more than 20 years of development, involving thousands of scientists, engineers, and technicians from NASA, the European Space Agency, and the Canadian Space Agency. Its total cost approached $10 billion, making it one of the most expensive scientific instruments ever built. It was launched on December 25, 2021, Christmas Day, aboard an Ariane 5 rocket from the Guiana Space Center in French Guiana. And its destination was not low Earth orbit like Hubble. It traveled to the second Lagrange point, or L2, a gravitationally stable location approximately 1.5 million kilometers from Earth, about 4 times the distance to the Moon. At L2, the telescope orbits the Sun in synchrony with the Earth, always keeping the Earth, Sun, and Moon behind it. This is crucial because JWST observes in infrared, and infrared is essentially heat radiation. Everything that is warm emits infrared light. To detect the incredibly faint infrared light from galaxies billions of light-years away, the telescope itself must be kept extraordinarily cold. Otherwise, its own heat would drown out the signal. JWST's instruments operate at temperatures around minus 233 degrees Celsius, or 40 Kelvin. Its mid-infrared instrument, MIRI, is cooled even further, to just 7 Kelvin, 7 degrees above absolute zero. To achieve these temperatures, JWST is equipped with a sunshield the size of a tennis court, approximately 21 meters by 14 meters. The sunshield consists of 5 layers of a material called Captain, coated with aluminum and silicon. These layers are separated by vacuum gaps, and each layer blocks and re-radiates heat, so that by the time you reach the 5th layer, the temperature has dropped from the scorching heat of direct sunlight to the frigid cold required by the instruments. The sunshield always faces the Sun, Earth, and Moon, keeping them on one side, while the telescope's mirrors and instruments sit in the permanent shadow on the other side. It is an engineering marvel of the highest order. The telescope's primary mirror is 6.5 meters across, compared to Hubble's 2.4 meters. This gives JWST about 6.25 times the light collecting area of Hubble, allowing it to detect much fainter objects. But the mirror posed one of the greatest engineering challenges of the project. It was too large to fit inside any existing rocket fairing in one piece. So it was designed to fold. The primary mirror is composed of 18 hexagonal segments, each one 0.32 meters across and weighing approximately 20 kilograms. Each segment is made of beryllium, a lightweight, strong metal that holds its shape well at cryogenic temperatures, and is coated with a thin layer of gold, which is an excellent reflector of infrared light. After launch, the mirror segments unfolded and were aligned with nanometer precision using tiny actuators behind each segment. The alignment process took weeks, and it achieved an accuracy far exceeding the minimum requirements. The mirror is so precisely shaped that if you scaled it up to the size of the continental United States, the largest bump would be only a few inches tall. JWST carries 4 main scientific instruments. NIR-CAM, the near-infrared camera, is the primary imaging instrument and covers wavelengths from 0.6 to 5 microns. It provides the stunning images you have seen of nebulae, galaxies, and deep fields. It is also used for wavefront sensing, the process of monitoring and correcting the alignment of the primary mirror segments. NIR-SPEC, the near-infrared spectrograph, can observe the spectra of up to 100 objects simultaneously using a micro-shutter array, a device with about 250,000 tiny shutters that can be individually opened or closed to select specific targets. This allows astronomers to study the chemical composition, distance, temperature, and motion of distant objects with extraordinary efficiency. MIRI, the mid-infrared instrument, covers longer wavelengths from 5 to 28 microns. It can see through dust that is opaque at shorter wavelengths, revealing hidden stars, protoplanetary disks, and the dusty cores of galaxies. And FGS/NIRISS, the fine guidance sensor and near-infrared imager and slitless spectrograph provided by Canada, is used for precision pointing and for spectroscopy of bright objects. The deployment of JWST was one of the most nerve-wracking events in the history of space science. There were 344 single points of failure, 344 things that had to work perfectly, with no backup, no redundancy, and no possibility of repair, since the telescope is 1.5 million kilometers away, far beyond the reach of any crewed mission. Every solar panel deployment, every sunshield layer separation, every mirror segment unfolding, every latching mechanism, they all had to work. And they all did. Every single one. It was a triumph of engineering, planning, and execution that will be studied and admired for generations. Now, here is where the story gets truly extraordinary. JWST was designed to find the first galaxies, small, dim, primitive objects forming in the first few 100 million years after the Big Bang. The models predicted that these earliest galaxies would be faint, irregular, and modest in size. After all, there had been very little time for galaxies to form and grow. According to the standard lambda-CDM model of cosmology, which describes a universe dominated by dark energy, lambda, and cold dark matter, CDM, galaxies form hierarchically. Small structures form first, then merge over time to create larger structures. The first galaxies were expected to be small building blocks, not fully formed cosmic metropolises. But almost as soon as JWST opened its golden eye and began observing, something unexpected happened. Something deeply unsettling for the standard model. JWST found galaxies that were too big, too bright, too massive, and too structured for how young the universe was when they existed. And not just one or two, dozens of them, everywhere it looked. The first hint came with JWST's very first deep field image, released on July 12, 2022. This image, centered on the galaxy cluster SMACS0723, was the deepest and sharpest infrared image of the distant universe ever taken. It showed thousands of galaxies, some of them among the most distant ever observed. And among those galaxies were objects that immediately raised eyebrows. Their light suggested they existed within the first few 100 million years after the Big Bang, but their brightness suggested they were far more massive than they should have been at that time. Over the following months, as more data poured in, the situation became clearer and more troubling. Teams of astronomers around the world began analyzing the JWST data, and paper after paper reported the same finding. There were far more bright, massive galaxies in the early universe than the standard model predicted. Some galaxies appeared to have stellar masses of billions of solar masses, existing at times when the universe was less than 500 million years old. The standard model said this was extremely unlikely, perhaps impossible. These galaxies should not have had enough time to accumulate so many stars. The raw materials were there. Gas was plentiful in the early universe, but the processes of gas cooling, collapse, and star formation were supposed to be too slow to produce such massive galaxies in such a short time. The headlines were dramatic. Scientific American declared, JWST discovers enormous distant galaxies that should not exist. Astronomy magazine announced, we just discovered the impossible, and the scientific community entered a period of intense debate. Was the standard model broken? Did we need to fundamentally revise our understanding of cosmology? Or were there more mundane explanations that could account for the discrepancy? Let me take you through this crisis in detail, because understanding it is absolutely essential to understanding why the idea of a second Big Bang has gained so much traction. The first thing to understand is how astronomers determine the mass and distance of these early galaxies. When JWST observes a distant galaxy, it does not directly see how massive the galaxy is. What it sees is light, infrared light, stretched by the expansion of the universe. By analyzing this light, astronomers can determine two crucial things: how far away the galaxy is, which tells them how old it is since we are looking back in time, and how bright it is. The distance is determined by the galaxy's redshift, the amount by which its light has been stretched to longer wavelengths. A redshift of, say, z equals 10 means we are seeing the galaxy as it existed when the universe was about 500 million years old. A redshift of z equals 14 means we are seeing it when the universe was only about 280 million years old. The higher the redshift, the more distant the galaxy, and the younger the universe was when the light was emitted. Determining the galaxy's mass from its brightness is more complicated. The brightness of a galaxy depends on the number of stars it contains, the types of stars. More massive stars are brighter, the age of those stars. Young stars are brighter, and the amount of dust, which absorbs and re-emits light at different wavelengths. Astronomers use models, called spectral energy distribution models, to estimate the stellar mass of a galaxy from its observed brightness at different wavelengths. They compare the galaxy's observed light to a library of model galaxies with different combinations of stellar masses, ages, star formation rates, and dust content, and find the best match. But as Catherine Chworowski of the University of Texas at Austin explains, it's an estimation. It's not a direct observation. There are many assumptions built into these models, and different assumptions can lead to different mass estimates. And this is where some of the initial alarm began to be tempered. In the earliest JWST observations, the instruments were still being calibrated, and some of the initial photometric measurements of brightness, turned out to be slightly off. When the calibrations were refined, some of the mass estimates came down. Galaxies that had initially appeared impossibly massive became merely very massive. This solved part of the problem, but not all of it. There were still too many bright, early galaxies, and some of them stubbornly resisted explanation by calibration alone. Then came another piece of the puzzle. Some of the objects that had been initially classified as massive early galaxies turned out to be something else entirely, something completely unexpected. They were called little red dots. These are compact red objects that appeared in JWST images by the hundreds, scattered throughout the early universe. At first, they were mistaken for massive galaxies because of their brightness. But when astronomers obtained spectra of these objects, breaking their light into its component wavelengths to study their composition, they found something surprising. The little red dots showed signatures consistent not with vast collections of stars, but with supermassive black holes. Specifically, they appeared to be massive black holes in an extremely active growth phase, surrounded by hot, dense, dusty material. The black holes were accreting matter at prodigious rates, and this accretion process was producing the intense, red-shifted light that JWST was detecting. In other words, some of the impossible galaxies were not galaxies at all. They were black holes in disguise. But this discovery, while solving one mystery, created another. Because if these little red dots are supermassive black holes existing within the first 1 to 2 billion years of the universe, then how did such massive black holes form so quickly? In the local universe, supermassive black holes, with masses of millions to billions of solar masses, are found at the centers of virtually all large galaxies. But forming such a massive black hole takes time. If you start with a seed black hole formed from the collapse of a massive star, which might have a mass of a few tens of solar masses, it needs to accrete an enormous amount of material to grow to millions or billions of solar masses. And there are limits on how fast a black hole can accrete matter, the Eddington limit, imposed by the outward pressure of radiation on the infalling material. Under standard assumptions, it should take hundreds of millions to billions of years for a stellar mass black hole to grow into a supermassive one. But JWST is finding supermassive black holes at times when the universe was less than 1 billion years old. How did they grow so fast? This is one of the most important open questions in astrophysics, and several solutions have been proposed. One possibility is that the seed black holes were much more massive than we assumed. Perhaps formed not from ordinary stellar collapse, but from the direct collapse of massive gas clouds, producing direct collapse black holes, with initial masses of 10,000 to 100,000 solar masses. This would give them a huge head start. Another possibility is that the early black holes accreted matter at super-Eddington rates, faster than the standard limit, perhaps because the material was falling in from multiple directions simultaneously, or because the accretion geometry was different from what we assumed. And a third, more exotic possibility, one that has generated enormous excitement, is that the little red dots are not black holes inside galaxies at all, but a completely new type of object. Black hole stars. A black hole star would be a massive star with a small black hole at its core. The black hole would be slowly consuming the star from the inside out, and the star's enormous gravitational binding energy would be converted into radiation, making the object extraordinarily luminous. This is a radical speculative idea, but it has the advantage of naturally explaining both the compact size and the extreme brightness of the little red dots. As of early 2026, this remains an active area of research, with new data from JWST continuing to refine our understanding of these mysterious objects. Now, setting the little red dots aside, there is still the fundamental issue of the overabundance of bright, massive early galaxies. Even after accounting for calibration refinements and the reclassification of some objects as active black holes, JWST is finding more bright galaxies in the first billion years of the universe than standard models predict. How can we explain this? One leading explanation involves what astronomers call bursty star formation. In the standard models, star formation in galaxies is assumed to be relatively steady, a continuous process of gas cooling, collapsing, and forming stars at a more or less constant rate. But what if star formation in the early universe was not steady at all? What if it happened in intense bursts, brief periods of extremely rapid star formation followed by quieter periods? If we happen to be observing a galaxy during one of its bursts, it would appear much brighter than its average state, leading us to overestimate its mass. There is growing evidence from both observations and simulations that star formation in the early universe was indeed highly bursty, and this could account for a significant fraction of the discrepancy. Another explanation involves the initial mass function, or IMF, the distribution of masses among the stars that form in a galaxy. In the local universe, we observe that for every massive star that forms, many smaller stars form as well. The exact ratio is described by the IMF, and it has been measured empirically for nearby star-forming regions. But what if the IMF was different in the early universe? What if, in the primordial conditions of high gas density and low metallicity, a larger proportion of massive stars formed relative to smaller stars? This would be called a top-heavy IMF. More massive stars are dramatically brighter than smaller stars. A star 10 times the mass of the Sun is not 10 times brighter but thousands of times brighter. So, a galaxy with a top-heavy IMF would appear much brighter than a galaxy with the same total mass, but a normal IMF. This means the early galaxies might not actually be as massive as their brightness suggests. They might just have a higher proportion of very bright, massive stars. A third explanation relates to the density of gas in the early universe. The early universe was smaller and more compressed than it is today. Gas was denser. Denser gas can collapse and form stars more quickly than less dense gas. If the rate of star formation in the early universe was faster than models assumed, because the gas was denser, then the early appearance of bright galaxies would be less surprising. As Catherine Chorowski explains, we know the universe early on was very dense. Gas that is dense does form stars faster, because more dense gas can collapse more easily, and that's how star formation happens. And a fourth explanation involves dust. Dust absorbs light, particularly at shorter wavelengths. If early galaxies had less dust than we assumed, then less of their light would be absorbed, and they would appear brighter to us. This would lead us to overestimate their mass. The amount of dust in the very early universe is not well constrained, and it is plausible that the first generations of galaxies had significantly less dust than later ones. Each of these explanations can account for part of the discrepancy. It is likely that the truth involves some combination of all of them. And importantly, none of these explanations require throwing out the Big Bang Theory or the standard model of cosmology. As Dr. Jehan Kartaltepe of the Rochester Institute of Technology, leader of the Cosmos Web Survey, says, "So far, it seems everything can still be explained with our cosmological model and our understanding of when the Big Bang happened. It just needs some fine-tuning. It shines a flashlight on where we didn't understand things." But while these explanations may account for the numbers of bright galaxies, they do not fully explain all of JWST's surprising findings. There are deeper mysteries that require us to think more radically, and the most profound of these mysteries was revealed in January 2026, with the confirmation of the most distant galaxy ever observed. The galaxy is called MOM-Z14. It was confirmed by a team led by Dr. Rohan Naidu from the Kavli Institute, using spectroscopic observations from JWST. Spectroscopy is the gold standard for measuring distances in astronomy. It involves breaking a galaxy's light into its component wavelengths and measuring the precise positions of spectral lines, bright or dark features at specific wavelengths corresponding to specific elements. By comparing these positions to where the lines would appear in a laboratory, astronomers can determine exactly how much the light has been redshifted, and therefore how far away the galaxy is. For MOM-Z14, the spectroscopic redshift was measured at Z equals 14.4. This means we are seeing this galaxy as it existed just 280 million years after the Big Bang. Just 280 million years. The universe was barely a toddler, cosmically speaking. And yet there it was, a galaxy. Not just a faint smear of light, but a luminous, compact object with detectable spectral features. Its radius is approximately 300 light-years. Tiny compared to the Milky Way's 100,000 light-year diameter, but astonishingly bright for its size and age. But here is what makes MOM-Z14 truly revolutionary. When astronomers analyzed its spectrum, they found something that should not have been there: nitrogen. Specifically, nitrogen emission features indicating a far higher abundance of nitrogen than normal stellar processes could have produced in just 280 million years. In normal stellar evolution, nitrogen is produced through the CNO cycle, carbon-nitrogen-oxygen cycle, a nuclear fusion process that occurs in stars. But producing the amount of nitrogen observed in MOM-Z14 through ordinary stars would take far longer than 280 million years. The nitrogen abundance was too high. Far too high. And there is only one known way to produce such extreme levels of nitrogen so quickly: supermassive primordial stars. Monster stars. Stars between 1,000 and 10,000 times the mass of our Sun. These monster stars, a subset of the theoretical population 3 stars, would have been unlike anything that exists in the universe today. They would have been enormous, potentially millions of times brighter than our Sun. They would have burned through their hydrogen fuel at a prodigious rate, using the CNO cycle to fuse hydrogen into helium. And the CNO cycle produces nitrogen as a byproduct. The more massive the star, the more efficient the CNO cycle, and the more nitrogen is produced. For stars of 1,000 to 10,000 solar masses, the nitrogen production would be exactly in the range needed to explain the observations in MOM-Z14. This was confirmed by a study published in September 2025, led by astronomers from the Harvard-Smithsonian Center for Astrophysics, who found the first direct evidence of monster stars in the galaxy GS3073 at redshift Z equals 5.55. The nitrogen excess in GS3073 could only be explained by primordial stars of extreme mass. And then, in January 2026, the same nitrogen signature was found in MOM-Z14, the most distant galaxy ever observed. Avi Loeb, a prominent astrophysicist at Harvard, published an analysis noting that the nitrogen features in MOM-Z14 cannot be produced by normal stars within 280 million years after the Big Bang, and that they point unambiguously to the existence of supermassive population 3 stars at the cosmic dawn. If confirmed by further observations, this is one of the most important discoveries in the history of astronomy. Population 3 stars have been predicted by theory for decades, but they have never been directly observed. They are one of the holy grails of astrophysics. Finding their chemical fingerprints in the most distant galaxy ever observed brings us closer to that holy grail than we have ever been. And it tells us something profound about the early universe. It was not the quiet, simple place we had imagined. It was a place of extremes, extreme temperatures, extreme densities, extreme stellar masses, a violent, dynamic crucible in which the seeds of all future cosmic structure were being forged. And speaking of the previous record holder for the most distant galaxy, that was JADES-GS-Z14-0, confirmed at a redshift of approximately 14.32, corresponding to about 290 million years after the Big Bang. That galaxy, discovered by the JWST Advanced Deep Extragalactic Survey Team, was itself a stunning achievement. It was also surprisingly bright and luminous for its age. The discovery of MOM-Z14 pushed the observational frontier even further, by an additional 10 million years closer to the Big Bang. Each new record-breaking galaxy brings us closer to the very first objects that formed in the universe, and each one teaches us something new about the conditions of the cosmic dawn. But the surprises do not stop there. In early 2025, JWST delivered another shock: the discovery of the Big Wheel Galaxy. This is a massive galaxy with a well-defined spiral structure, existing within the first 2 billion years of the universe. Now, spiral galaxies are common in the local universe. Our own Milky Way is a spiral galaxy, but spiral structure takes time to develop. It requires a galaxy to be rotating in an orderly fashion, with a thin disk of stars and gas. And orderly rotation is disrupted by violent events like galaxy mergers, which were much more common in the early universe when galaxies were closer together. Mergers tend to destroy spiral structure, converting spirals into elliptical galaxies with smooth, featureless shapes. So, finding a spiral galaxy in the early universe was surprising. Finding a massive, well-defined spiral galaxy was astonishing. The Big Wheel, as the researchers named it, appears to have maintained its delicate spiral arms, despite existing in a crowded, merger-rich environment. Dr. Themia Nanayakara of Swinburne University of Technology, one of the discoverers, noted, "The fact that this galaxy didn't become elliptical means that there might be ways that galaxies can grow that we haven't encountered in the local universe." This suggests that galaxy growth in the early universe may have involved processes, perhaps smooth accretion of gas from filaments of the cosmic web, rather than violent mergers that our current models do not fully capture. If you are still here, if you have been following this journey from the first fraction of a second after the Big Bang to the most distant galaxies ever observed, then you are exactly the kind of person this channel was made for. You are a deep thinker, a cosmic explorer, and I appreciate you being here. Before we continue to the most mind-bending part of this video, the dark Big Bang theory, take a moment. Drop a comment below. Tell me, what has surprised you the most so far? What has made you rethink something you thought you knew? And if you have not subscribed yet, now is the time. What comes next is going to change how you see the universe. Let us talk about dark stars. This is one of the most exotic and fascinating ideas to emerge from the age of JWST, and it directly connects to the question of a second Big Bang. The concept of dark stars was proposed by Catherine Fries, the same physicist who later proposed the dark Big Bang theory, along with her colleagues beginning in 2007. The idea is this: in the very early universe, when the first stars were forming from primordial gas clouds, dark matter was also present in large quantities. In fact, dark matter was concentrated in dense clumps, dark matter halos, and it was the gravity of these dark matter halos that pulled the primordial gas together in the first place, enabling the first stars to form. Now, if dark matter is made of particles that can annihilate each other, a process in which a dark matter particle meets its antiparticle, and both are converted into energy, then in the dense environments where the first stars formed, dark matter annihilation could have produced enormous amounts of energy. This energy could have heated the gas cloud, preventing it from collapsing under its own gravity and forming a normal star. Instead, the cloud would have remained in a stable, puffed-up state, supported by the energy from dark matter annihilation. The result would be a dark star, not a normal star powered by nuclear fusion, but a gigantic, fluffy, luminous object powered by the annihilation of dark matter in its core. Dark stars, if they existed, would have been truly extraordinary objects. They could have grown to be enormously massive, potentially millions of times the mass of the Sun, and extraordinarily luminous, potentially billions of times brighter than the Sun. They would have been much larger than normal stars, with radii that could rival the orbit of Earth around the Sun or even larger. And because they were powered by dark matter annihilation rather than nuclear fusion, they could have persisted for very long periods, potentially hundreds of millions of years, as long as there was dark matter available to fuel them. Eventually, when the supply of dark matter was exhausted, a dark star would collapse under its own gravity and potentially form a massive black hole, a seed for the supermassive black holes we observe at the centers of galaxies today. For years, dark stars remained a theoretical curiosity, an interesting idea, but one that could not be tested, because we lacked the technology to observe the early universe with sufficient detail. Then JWST arrived, and the situation changed dramatically. In 2023, Fries and her colleagues published a landmark paper suggesting that some of the objects JWST had identified as impossibly massive early galaxies might actually be supermassive dark stars. The reasoning was compelling. A single supermassive dark star, millions of times the mass of the Sun and billions of times brighter, could easily be mistaken for an entire galaxy in JWST images. The fuzzy blobs of light that astronomers were interpreting as distant galaxies with billions of stars could, in some cases, be individual dark stars, single objects masquerading as galaxies. In October 2025, this idea took a dramatic step forward. A team of researchers identified 4 spectroscopic dark star candidates in JWST data. Spectroscopic candidates are far more convincing than photometric candidates because spectroscopy provides detailed information about the object's composition and physical properties, not just its brightness. One of the 4 candidates was at redshift 14, among the most distant objects ever observed, existing just 300 million years after the Big Bang. The researchers used JWST's NIR-SPEC instrument to analyze the spectra of these objects, and found that their properties were consistent with supermassive dark stars, rather than typical early galaxies. This does not prove they are dark stars. Further observations are needed, but it puts the dark star hypothesis on much firmer observational footing. And then, in January 2026, another paper was published showing that dark stars could simultaneously solve 3 of the most puzzling observations of the high redshift universe: the existence of blue monster galaxies, extremely bright, blue objects in the early universe, the abundance of early supermassive black holes, and the overabundance of bright early objects in general. If dark stars were common in the early universe, they would naturally produce all 3 of these phenomena. They would appear as bright blue objects, blue monster galaxies. When they collapsed, they would leave behind massive black hole seeds, explaining early supermassive black holes. And their extreme luminosity would contribute to the apparent overabundance of bright objects. One theory, 3 problems solved. That is the hallmark of a powerful scientific idea. Now, if dark stars are powered by dark matter annihilation, this tells us something crucial about dark matter itself. It must be made of particles that can annihilate each other. This constrains the possible identities of dark matter particles and connects the dark star hypothesis directly to particle physics. and it connects in a deep way to the question of the dark Big Bang. Because the dark Big Bang theory proposes that dark matter was created in a separate cosmic event, and the nature of that event determines the properties of dark matter particles, including whether or not they can annihilate each other. The dark star and dark Big Bang hypotheses are not competing theories. They are complementary pieces of a potentially grand unified picture of the early universe. Before we get to the dark Big Bang itself, let me tell you about one more stunning JWST discovery that sets the stage perfectly. In December 2025, JWST confirmed the earliest supernova ever detected. A supernova is the explosive death of a massive star, one of the most violent events in the universe. This particular supernova was linked to a gamma-ray burst designated GRB 250314A, which was detected on March 14, 2025, by space-based gamma-ray observatories. Gamma-ray bursts are the brightest electromagnetic events in the universe. They can outshine an entire galaxy for a brief period. GRB 250314A was an extraordinary burst, and astronomers quickly coordinated follow-up observations to identify its source. Within 4 hours of the detection, the European Southern Observatory's Very Large Telescope in Chile obtained an estimate of the object's distance, suggesting it existed approximately 730 million years after the Big Bang. This was extraordinary, far earlier than any previously confirmed supernova. But ground-based telescopes could only go so far. To confirm the result and study the supernova in detail, they needed JWST. JWST observed the location of GRB 250314A using its near-infrared camera, NIR-CAM, and the results were stunning. The telescope captured a clear image of the supernova, the light from a single star that exploded when the universe was just 730 million years old. It also identified the supernova's host galaxy, an extremely faint collection of star clusters, revealing a tiny young galaxy in the process of forming its first generations of stars. The supernova had occurred during the epoch of reionization, when the universe was still being ionized by the radiation from the first stars and galaxies. This single observation proved several things at once. That massive stars were already forming within the first billion years of the universe. That these massive stars were already dying in spectacular supernova explosions, and that these explosions were producing gamma-ray bursts, some of the most energetic events in the cosmos. The previous record for the earliest known supernova was one that occurred when the universe was 1.8 billion years old. GRB 250314A shattered that record, pushing it back by over 1 billion years. This discovery is deeply relevant to our story for a specific reason. The supernova that produced GRB 250314A was almost certainly a very massive star, likely many tens of solar masses at minimum, because only the most massive stars produce the type of supernova that generates a gamma-ray burst. This adds to the growing body of evidence from JWST that the early universe was home to extremely massive stars, possibly including the monster stars and population 3 stars we discussed earlier. And the chemical elements produced by such supernovae, including heavy elements like iron, nickel, and others, were seeded into the surrounding gas, enriching it for the next generation of star formation. Every supernova in the early universe was a step in the long chain of cosmic chemistry that eventually produced the elements necessary for rocky planets and, ultimately, for life. Now, finally, let us talk about the dark Big Bang. This is the core of our story. This is the idea that has the potential to reshape our understanding of the origin of the universe. And I'm going to explain it to you from the ground up, so that by the end of this section you understand not just what the theory says, but why it was proposed, what evidence supports it, how it could be tested, and what it would mean if it turns out to be true. The story of the dark Big Bang begins with a mystery. The mystery of dark matter. We have discussed dark matter several times already, but now we need to confront it directly, because this mystery is at the heart of the dark Big Bang theory. Dark matter is the most abundant form of matter in the universe. It outweighs ordinary matter, the protons, neutrons, and electrons that make up atoms, by a factor of about 5 to 1. For every kilogram of ordinary matter in the universe, there are approximately 5 kilograms of dark matter. This is not speculation. The evidence for dark matter's existence is overwhelming, coming from multiple independent lines of observation. The first line of evidence comes from galaxy rotation curves. In the 1970s, astronomer Vera Rubin studied the rotation speeds of stars and gas clouds at different distances from the centers of galaxies. According to Newtonian gravity, objects farther from a galaxy's center should orbit more slowly, just as the outer planets in our solar system orbit the Sun more slowly than the inner planets. But Rubin found that the rotation speeds remained roughly constant, or even increased, at large distances from the center. This flat rotation curve could only be explained if galaxies were embedded in a vast, invisible halo of additional mass that extended far beyond the visible disk. This invisible mass is dark matter. The second line of evidence comes from gravitational lensing, the bending of light from distant objects by the gravity of foreground matter. When a massive galaxy cluster sits between us and a more distant galaxy, the cluster's gravity bends the distant galaxy's light, distorting and magnifying its image. The amount of bending depends on the total mass of the cluster. When astronomers measured the bending, they found that the clusters were far more massive than the visible matter stars and gas could account for. The extra mass is dark matter. The third line of evidence comes from the cosmic microwave background. The tiny fluctuations in the CMB, the variations of a few millionths of a degree in the temperature of the afterglow radiation, encode information about the composition of the early universe. By analyzing these fluctuations with incredible precision, the WMAP and Planck satellites determined the proportions of ordinary matter, dark matter, and dark energy in the universe. The result? Ordinary matter is about 5%, dark matter is about 27%, and dark energy is about 68%. These measurements are consistent with all other evidence for dark matter and constrain its abundance with high precision. The fourth line of evidence comes from the large-scale structure of the universe. Computer simulations of the formation and evolution of cosmic structure. The vast web of galaxies, galaxy clusters, filaments, and voids that define the large-scale organization of the universe only reproduce the observed structure if they include dark matter. Without dark matter, galaxies and galaxy clusters do not form in the right places, at the right times, or with the right properties. Dark matter provides the gravitational scaffolding on which the luminous structures of the universe are built. The fifth line of evidence comes from the bullet cluster, a pair of galaxy clusters that collided and passed through each other. In the collision, the hot gas from each cluster, which constitutes most of the ordinary matter, was slowed down by friction and got stuck in the middle. But gravitational lensing maps show that most of the mass is not in the middle. It is on the outskirts, having passed through without friction. This is exactly what you would expect if most of the mass were made of dark matter, which does not interact with ordinary matter, or with itself, through any force except gravity. The dark matter just sailed through the collision, while the ordinary gas got stuck. This observation is considered one of the most direct pieces of evidence for the existence of dark matter as a separate form of matter. So the evidence that dark matter exists is beyond any reasonable doubt. The question is, what is it? And this is where things get deeply frustrating, because despite knowing that dark matter exists and knowing how much of it there is, we have absolutely no idea what it is made of. We know what it is not. It is not ordinary matter. It is not made of protons, neutrons, or electrons. It does not interact with light. It neither emits, absorbs, nor reflects electromagnetic radiation of any kind. It does not interact with ordinary matter through the electromagnetic force or the strong nuclear force. The only force through which it reliably interacts is gravity, and this makes it extraordinarily difficult to detect directly. For decades, the leading candidate for dark matter particles was a class of hypothetical particles called WIMPs, weakly interacting massive particles. WIMPs were attractive because they arose naturally from extensions of the standard model of particle physics, particularly supersymmetry, and because the predicted abundance of WIMPs from the early universe was in the right ballpark to account for the observed amount of dark matter, a coincidence known as the WIMP miracle. Enormous experimental efforts were mounted to detect WIMPs. Underground detectors like Lux, Xenon, Panda X, and others buried deep beneath rock to shield them from cosmic rays, waiting for a dark matter particle to occasionally bump into a nucleus of ordinary matter and produce a detectable signal. Particle accelerators like the Large Hadron Collider at CERN attempted to create dark matter particles by smashing protons together at nearly the speed of light. And astrophysical observations searched for the products of dark matter annihilation, gamma rays, positrons, antiprotons that should be produced if WIMPs annihilate each other in regions of high dark matter density. But after decades of increasingly sensitive searches, the result has been the same. Nothing. No WIMPs have been detected. The underground detectors have seen no signal above background noise. The LHC has found no evidence for supersymmetric particles. The astrophysical searches have produced ambiguous results at best. The WIMP is, if not dead, at least seriously wounded. This persistent failure to detect dark matter directly is one of the greatest puzzles in modern physics. And it is this failure that motivated Catherine Freese and Martin Winkler to propose the dark Big Bang theory. Their reasoning was elegant. If dark matter does not interact with ordinary matter through any force except gravity, then maybe it was never created alongside ordinary matter in the first place. Maybe it has a completely separate origin. Maybe it was created in its own Big Bang, a dark Big Bang, through physics that has nothing to do with the physics of ordinary matter. And if that is the case, then of course our detectors, which are designed to catch interactions between dark matter and ordinary matter, would find nothing, because there are no such interactions. Dark matter and ordinary matter are strangers, born in different cosmic events, connected only by the universal force of gravity. The dark Big Bang theory was first proposed in a paper published in February 2023. Freese, who is the director of the Texas Center for Cosmology and Astroparticle Physics at the University of Texas at Austin, and Winkler, also at the University of Texas, presented a scenario in which the universe experienced two creation events. The first was the standard Big Bang, which created ordinary matter, protons, neutrons, electrons, photons, and all the particles described by the standard model of particle physics. The second was a dark Big Bang, which created dark matter. The dark Big Bang, they proposed, could have occurred anywhere from a few weeks to about a month after the standard Big Bang. It was driven by a separate quantum field, distinct from the inflaton field that drove cosmic inflation, and distinct from the Higgs field that gives ordinary particles their mass. This field, which we might call the dark field, existed in a metastable state, a state that was stable but not the lowest energy state. At some point, the dark field underwent a phase transition, a sudden change of state analogous to water freezing into ice. And this phase transition released an enormous amount of energy. This energy was converted into dark matter particles, flooding the universe with the invisible substance that would go on to shape the formation of galaxies, stars, and large-scale cosmic structure. But because this energy was released entirely within the dark sector, the set of dark matter particles and their interactions, it did not produce any ordinary matter. No photons, no protons, no electrons, just dark matter. And this dark matter interacted with ordinary matter only through gravity, exactly as we observe. The beauty of this theory lies in its explanatory power. It naturally explains why dark matter has never been detected directly, because it was created through entirely different physics in a separate cosmic event, and it interacts with ordinary matter only gravitationally. It explains why the WIMP miracle failed, because WIMPs were predicted to interact with ordinary matter through the weak nuclear force. But if dark matter was created in a dark Big Bang, there is no reason it should have any non-gravitational interactions with ordinary matter at all. And it is consistent with all existing observational constraints, including the abundances of light elements from Big Bang nucleosynthesis and the temperature fluctuations of the cosmic microwave background. The dark Big Bang, if it happened soon enough, within a few months of the standard Big Bang, would not have affected these observables because they were already essentially locked in by the time the dark Big Bang occurred. Now, the theory became even more compelling in December 2024, when two scientists from Colgate University, Cosmini Lee, an assistant professor of physics and astronomy, and Richard Casey, published a major expansion of the dark Big Bang theory in the journal Physical Review D. Ely and Casey systematically explored the full mathematical parameter space of the dark Big Bang scenario, identifying all the possible ways in which the theory could be realized while remaining consistent with observational constraints. Their results were striking. They found that the dark Big Bang has many more possible realizations than those identified by Friis and Winkler in their seminal work. In other words, the theory is not just one specific scenario. It is a large family of scenarios, all of which are consistent with what we know about the universe. The dark Big Bang could have occurred simultaneously with the standard Big Bang, or it could have occurred up to 1 year later. It could have produced dark matter particles of various masses and properties, and it could have given rise to a rich, dark sector, a whole hidden world of dark matter particles and dark forces that we cannot access except through gravity. Ely explained the philosophical motivation behind the theory. The assumption that dark matter and regular matter originated in the same event, the Big Bang, is natural, given its simplicity. That is why it remained unchallenged for so long. However, nature does not need to be parsimonious, abide by Occam's razor, or by any of our aesthetic preferences. This is a profound point. Occam's razor, the principle that the simplest explanation is usually the best, is a useful guideline, but it is not a law of nature. The universe is under no obligation to be simple, and the persistent failure to detect dark matter, despite decades of effort and billions of dollars of investment, suggests that perhaps the simplest explanation is wrong, and the truth is more complex. Casey added another thought-provoking dimension to the theory. Who is to say that dark matter, all the yet undiscovered particles that make up most of the universe, does not have its own complicated set of particles and interactions? In other words, the dark sector might not just be a single type of particle. It might be a whole parallel physics, with its own forces, its own particles, its own structures. Just as ordinary matter has protons, neutrons, electrons, photons, gluons, quarks, neutrinos, and a host of other particles interacting through electromagnetism, the strong force and the weak force, the dark sector might have its own menagerie of particles interacting through forces we cannot detect. And all of this would have been created in the dark Big Bang. One of the most exciting aspects of the Ely and Casey work is that it provides a roadmap for how the dark Big Bang could be detected. The key is gravitational waves. An event as violent as a dark Big Bang, a phase transition of a cosmic scalar field, releasing enormous energy into the dark sector, would have generated gravitational waves. Gravitational waves are ripples in the fabric of space-time itself, first predicted by Einstein in 1915, and first directly detected by the LIGO Observatory in 2015, from the merger of two black holes. The gravitational waves from a dark Big Bang would have a distinctive signature, a background hum at specific frequencies, different from the gravitational waves produced by merging compact objects. And crucially, Ely and Casey showed that for certain parameter choices, these gravitational waves fall within the sensitivity range of current or upcoming experiments. The International Pulsar Timing Array, or IPTA, is a collaboration of radio telescopes around the world that monitors millisecond pulsars, rapidly spinning neutron stars that emit radio pulses with extraordinary regularity, like cosmic clocks. Gravitational waves passing between the pulsars and Earth would cause tiny, correlated variations in the arrival times of the pulses. By monitoring many pulsars simultaneously, the IPTA can detect the gravitational wave background, the cumulative signal of all gravitational wave sources in the universe. In 2023, the Nanograv experiment, one component of the IPTA, reported evidence for such a background, a low-frequency hum permeating the cosmos. The source of this background is not yet confirmed, but one possibility is that it includes a contribution from the dark Big Bang. If the signal can be analyzed in sufficient detail, it might be possible to identify a component with the spectral characteristics predicted by the dark Big Bang theory. The Square Kilometre Array, or SKA, is a next-generation radio telescope array currently under construction in Australia and South Africa. When complete, it will be the most sensitive radio telescope ever built, with a total collecting area of approximately 1 square kilometer, hence the name. The SKA will dramatically improve the precision of pulsar timing, making it a far more powerful tool for detecting gravitational waves at the frequencies relevant to the dark Big Bang. And looking further into the future, the Laser Interferometer Space Antenna, or LISA, is a European Space Agency mission planned for launch in the 2030s. LISA will be a space-based gravitational wave detector, 3 spacecraft arranged in an equilateral triangle with sides of 2.5 million kilometers, using laser interferometry to detect the stretching and squeezing of spacetime caused by passing gravitational waves. LISA will be sensitive to frequencies much lower than the ground-based LIGO and Virgo detectors, opening up a new window on the gravitational wave universe. It could potentially detect the gravitational wave signature of a dark Big Bang, providing direct evidence for this extraordinary cosmic event. If the gravitational wave signature of the dark Big Bang is detected, and I want to emphasize that this is a real, testable prediction, not a vague hope, it would be one of the most profound discoveries in the history of science. It would tell us that the origin of the universe was not a single event, but at least 2 events. It would tell us that the matter we are made of and the matter that holds galaxies together have completely different origins. It would tell us that there is an entire hidden sector of physics, a dark sector, with its own creation story, its own particles, and its own interactions. And it would fundamentally alter our understanding of the first moments of cosmic history. Now, I want to be very clear about what JWST has and has not done in relation to the dark Big Bang theory. JWST has not directly detected a second Big Bang. It has not found a smoking gun, an unambiguous piece of evidence that says, yes, this happened. What JWST has done is create the observational context that makes the dark Big Bang theory necessary and plausible. By finding galaxies that are too massive, too bright, and too structured for the standard model, by discovering evidence for monster stars, dark stars, and early supermassive black holes, by pushing the observational frontier to just 280 million years after the Big Bang, and by revealing an early universe that is far more complex and dynamic than anyone expected, JWST has shown us that our understanding of the early universe is incomplete, and the dark Big Bang is one of the most promising and elegant proposals for what might be missing. Furthermore, JWST observations are being used directly to test dark matter models. In December 2025, researchers from Arizona State University published results showing that JWST data can distinguish between different models of dark matter, cold dark matter, warm dark matter, and wave dark matter, through their effects on the structure of early galaxies. If dark matter was created in a dark Big Bang rather than in the standard Big Bang, this would affect its properties, its mass, its temperature, its interactions, and leave observable signatures in the galaxies that JWST is studying. The interplay between JWST observations and dark matter theory is one of the most dynamic and exciting areas of astrophysics right now, and it is bringing us closer to understanding the nature of dark matter than ever before. Let me also address how the dark Big Bang compares to other dark matter origin theories, because it is important to see it in context. The standard WIMP hypothesis, as we discussed, proposes that dark matter was created in the standard Big Bang and consists of particles that interact weakly with ordinary matter. This hypothesis is being increasingly constrained by negative experimental results. Axions are another candidate. Ultralight particles predicted by certain extensions of the standard model, which could be produced in the early universe and accumulate in galaxy halos. Several experiments, including ADMX, Axion Dark Matter Experiment, are searching for axions, but no confirmed detection has been made. Primordial black holes, small black holes formed from density fluctuations in the early universe, are yet another candidate, and JWST observations of the early universe can help constrain their abundance. Sterile neutrinos, self-interacting dark matter, SIDM, and fuzzy dark matter are other proposals, each with distinct observational signatures. What makes the dark Big Bang unique among these theories is that it is not just a proposal for what dark matter particles are. It is a proposal for an entirely new cosmological event, a new chapter in the story of the universe's origin. It changes the timeline of cosmic history. It adds a second creation event, and it does so in a way that is mathematically rigorous, consistent with observations and, crucially, testable. If the gravitational wave signature is found, it confirms the theory. If it is not found within the predicted parameter range, it constrains or potentially rules out the theory. This falsifiability is the hallmark of good science. Now, I want to take you on a detour, a necessary one, into the alternative theories that address the same deep questions. Because the dark Big Bang is not the only radical idea that has been proposed to explain the mysteries of the early universe. There are other theories, some of them even more mind-bending, that challenge the very concept of the Big Bang as a unique, unrepeatable event. The first is the Big Bounce theory. The Big Bounce proposes that the Big Bang was not the absolute beginning of the universe, but rather a transition from a previous phase. Specifically, it suggests that a previous universe was contracting, getting smaller, denser, and hotter, and when it reached an extremely dense state, it bounced back into expansion. Our Big Bang was the bounce. This idea has a long history, going back to the early days of general relativity, but it fell out of favor because classical general relativity predicts a singularity, a point of infinite density, at the moment of the bounce, and physics breaks down at a singularity. However, in recent decades, new approaches to quantum gravity, particularly loop quantum gravity, LQG, have shown that quantum effects could prevent a true singularity from forming. In LQG, space is not infinitely divisible, but has a minimum granularity at the Planck scale. This granularity creates a repulsive force at extremely high densities, which would halt the collapse and cause a bounce. The mathematics of loop quantum cosmology, the application of LQG to the very early universe, show that a bouncing universe is not only possible, but natural. Paul Steinhardt of Princeton University and Neil Turok have developed elaborate bouncing cosmology models, including the ekpyrotic model, which draws on ideas from string theory. In the ekpyrotic scenario, the Big Bang was caused by the collision of higher dimensional membranes, in a higher dimensional space. The collision releases enormous energy, creating the hot, dense conditions of the Big Bang, and the branes then move apart, cool down, and eventually come together again for another collision. This leads naturally to a cyclic universe, one in which the Big Bang and Big Crunch alternate in an endless cycle of expansion and contraction. The cyclic universe model is perhaps the most philosophically striking alternative to the standard Big Bang. In this model, there is no beginning and no end. The universe has always existed, going through eternal cycles of bang, expansion, cooling, contraction, crunch, and bounce. Each cycle produces a new universe with its own stars, galaxies, and possibly life. The laws of physics might be the same in each cycle, or they might be slightly different. We do not know. The cyclic model avoids the uncomfortable question of what came before the Big Bang by replacing it with the previous cycle, and it avoids the equally uncomfortable question of what happens at the end by answering the next cycle begins. Interestingly, in October 2025, a new paper by Cornell physicist Henry Tai provided a calculation suggesting that the current expansion of the universe might eventually slow down and reverse, leading to a big crunch approximately 20 billion years from now. If this is correct, it would mean the universe is currently in the expansion phase of a cycle, and will eventually contract and perhaps bounce again. However, this remains highly speculative, and the mainstream view, based on the observed accelerating expansion, is that the universe will continue expanding forever, eventually reaching a state of maximum entropy called the heat death. Another alternative comes from Nobel laureate Sir Roger Penrose, who proposed conformal cyclic cosmology, or CCC. In Penrose's model, the universe goes through infinite aeons. At the end of each aeon, the universe has expanded so enormously that all matter has decayed. All black holes have evaporated through Hawking radiation, and only massless particles, like photons, remain. In such a universe, there is no mass, no rest frame, and no meaningful way to measure distance or time. Mathematically, this state is conformally equivalent to the singularity of a Big Bang, so the end of one aeon seamlessly becomes the beginning of the next. It is an extraordinarily elegant idea. The universe essentially forgets its size and starts over. Penrose has even claimed to have found evidence for CCC in the cosmic microwave background, in the form of Hawking points, circular temperature anomalies that could be remnants of evaporating black holes from the previous aeon. These claims are controversial and not widely accepted, but they illustrate the kind of bold, creative thinking that the mysteries of the early universe demand. And then there is the multiverse. The multiverse is not a single theory, but a family of ideas that propose the existence of multiple universes beyond our own. One version, the eternal inflation model, developed by Alan Guth and Andre Linde, proposes that the cosmic inflation that occurred in the first fraction of a second of our universe did not stop everywhere at once. In most of space, inflation continues forever, creating an ever-expanding background of inflating space. But in scattered regions, inflation ends, and each such region becomes a separate pocket universe with its own Big Bang, its own physical constants, and its own cosmic history. Our observable universe is just one such pocket in an infinite, eternally inflating multiverse. In this framework, asking, "Why did the Big Bang happen?" is like asking, "Why did this particular bubble form in a boiling pot?" It is not a unique event, but one of infinitely many similar events occurring throughout an eternal, ever-expanding cosmos. The multiverse idea connects to the dark Big Bang in a provocative way. If our visible universe is just one pocket in a larger multiverse, then perhaps the dark matter in our universe was imported from a neighboring pocket, or created at the boundary between pockets, in what we call a dark Big Bang. This is speculative, of course, but it illustrates how the dark Big Bang theory fits into a broader landscape of ideas about the nature of the cosmos. In September 2025, a new and radical Big Bang model was proposed, suggesting that gravitational waves from the initial moments of the universe played a much larger role than previously thought. In this model, gravitational waves themselves, not dark matter and dark energy, were the primary drivers of galaxy and star formation. The model attempts to explain the large-scale structure of the universe without invoking dark matter or dark energy at all, replacing them with the effects of primordial gravitational waves. This is a bold and controversial idea, and it is far from widely accepted, but it demonstrates the extraordinary ferment of ideas that JWST's discoveries have triggered. The observational surprises of the past few years have opened the floodgates of theoretical creativity, and physicists are exploring possibilities that would have been unthinkable a decade ago. Now, let us step back and assess the evidence. Let us be honest, rigorous, and fair. Did James Webb Space Telescope detect a second Big Bang? What does the evidence actually say? I want to lay it out systematically, looking at both sides, because that is how science works. Science is not about cheerleading for your favorite theory. It is about following the evidence wherever it leads, even if it leads somewhere unexpected, or somewhere uncomfortable. Let us start with the evidence that supports the dark Big Bang theory. First, the persistent failure of direct dark matter detection experiments. For over 30 years, increasingly sensitive experiments have searched for dark matter particles interacting with ordinary matter. The detectors have become thousands of times more sensitive. The searches have covered a vast range of particle masses and interaction strengths, and they have found nothing. Zero. This is consistent with the dark Big Bang prediction that dark matter does not interact with ordinary matter through any force except gravity, because it was created in a separate cosmic event involving separate physics. Second, JWST's discovery of an early universe that is more complex, dynamic, and structure-rich than the standard model predicted. The impossible galaxies, monster stars, dark stars, little red dots, and early supermassive black holes all point to physics in the early universe that goes beyond the standard model. While these observations do not directly prove a dark Big Bang, they create an environment in which additional physics, possibly including a second creation event, is needed. Third, the mathematical consistency of the theory. Friis, Winkler, Ely, and Casey have shown that the dark Big Bang is consistent with all existing observational constraints, including Big Bang nucleosynthesis and the cosmic microwave background. It does not contradict any established observations. Fourth, the theory's testability. The dark Big Bang would have produced gravitational waves with a distinctive signature. Current and upcoming experiments, IPTA, Nanograv, SKA, LISA, are capable of detecting this signature. This means the theory can be confirmed or refuted by real data, which is the gold standard for scientific hypotheses. Fifth, the nanograv detection of a gravitational wave background. In 2023, the Nanograv collaboration reported evidence for a low-frequency gravitational wave background, a persistent hum of gravitational waves permeating the cosmos. The source of this background is not yet identified. It could be caused by supermassive black hole mergers, cosmic strings, or, intriguingly, a cosmological phase transition like the dark Big Bang. More data is needed to determine which interpretation is correct, but the possibility is tantalizing. Sixth, the broad parameter space. Ely and Casey showed that the dark Big Bang works across a wide range of parameters. It is not a finely tuned model that requires everything to be just so. This makes it more robust and more plausible. Now, let us look at the evidence against, or at least the reasons for caution. First, the dark Big Bang has not been directly confirmed. No gravitational wave signature uniquely attributable to a dark Big Bang has been identified. The theory remains a hypothesis, promising, elegant, and testable, but unconfirmed. Second, the JWST observations that motivated the theory may have more mundane explanations. Calibration refinements, bursty star formation, top-heavy IMF, and reduced dust content can each account for part of the discrepancy between observations and standard model predictions. It is possible that some combination of these effects fully explains the data without requiring new cosmology. Third, Occam's razor. The simplest explanation for the universe's origin is a single Big Bang. Adding a second Big Bang increases the complexity of the model. While Occam's razor is not an absolute principle, it is a useful guide, and any additional complexity needs to be justified by correspondingly strong evidence. Fourth, the theory does not specify what dark matter particles actually are. It tells us that dark matter was created in a separate event, but it does not predict the mass, spin, or interaction properties of dark matter particles. This means it cannot by itself guide experiments to detect dark matter directly. Fifth, the CMB constrains the theory. The cosmic microwave background has been measured with exquisite precision, and any theory of the early universe must be consistent with these measurements. The dark Big Bang currently passes this test, but future, more precise measurements could potentially rule it out. And sixth, the theory is very new. It was first proposed in 2023 and expanded in 2024. It has not yet been subjected to the decades of scrutiny and testing that the standard Big Bang theory has undergone. This does not mean it is wrong, but it means we should be cautious about accepting it prematurely. So, what is the honest answer to our question? Did James Webb detect a second Big Bang? The honest answer is not yet, not directly. But JWST has found a universe that is stranger, richer, and more complex than we expected. It has found galaxies that challenge our models, stars that defy our predictions, and objects that we do not yet fully understand. It has created an observational landscape in which the dark Big Bang theory is not just a wild speculation, but a serious, mathematically rigorous, testable hypothesis that addresses one of the deepest mysteries in physics. And within the next decade, possibly within the next few years, we will have the tools to test it definitively. That is not a failure. That is the cutting edge of science. That is how discovery works. Let me share one more thought from the scientists themselves, because their words capture the spirit of this moment beautifully. Catherine Chorowski, reflecting on the JWST discoveries, said, "It's not always a formula. There are times when you're going to see things that are outside of what you thought the path should be. That'll require you to revise things. It doesn't mean that the things you always said were wrong, but it does mean, oh, outliers. That's interesting. That's something that now needs to be folded in." And Themya Nanayakara, one of the discoverers of the Big Wheel Galaxy, said that JWST's findings are transformational, and that the groundbreaking observations have already been made. Now the challenge is to make sense of them. It'll be more fun now, trying to understand the physics as well. That attitude, curiosity without dogma, wonder without certainty, rigor without rigidity, is the essence of science, and it is the attitude that will carry us to the answer. Let us now zoom out from the specific scientific details and think about what all of this means. Not just for cosmology, not just for physics, but for us, for human beings, for our place in the universe, for our understanding of what it means to exist. Consider the sheer improbability of the chain of events that led to your existence. 13.8 billion years ago, the Big Bang, or the first Big Bang, created space, time, energy, and the fundamental particles of ordinary matter. Within the first few minutes, protons and neutrons fused into the nuclei of hydrogen and helium. For hundreds of millions of years, the universe was dark, just gas, slowly cooling, slowly clumping. Then the first stars ignited. Population 3 stars, possibly monster stars thousands of times more massive than our Sun, burned through their fuel in a cosmic instant and exploded, seeding the universe with carbon, oxygen, nitrogen, silicon, and iron. These elements mixed into the interstellar gas, enriching it for the next generation of stars. Generation after generation, stars were born and died, each one adding more heavy elements to the cosmic inventory. Eventually, about 9 billion years after the Big Bang, in an unremarkable corner of an unremarkable galaxy, a cloud of gas enriched by billions of years of stellar nucleosynthesis collapsed and formed a new star, our Sun. Around this new star, the leftover gas and dust coalesced into planets. On the third planet from the Sun, conditions happened to be just right for liquid water to exist. And in that water, through processes we still do not fully understand, the first self-replicating molecules appeared. Life. Over the next 4 billion years, life evolved from simple single-celled organisms into the staggering diversity of forms we see today, including one species that is curious enough, creative enough, and persistent enough to build a $10 billion telescope and point it at the edge of the observable universe, trying to understand where everything came from. And now, consider the role of dark matter in this story. Dark matter may have been created in a separate Big Bang, a dark Big Bang, through physics we do not yet understand. But dark matter's gravity was absolutely essential for the formation of the structures we see in the universe. Without dark matter, the tiny density fluctuations from the early universe would not have had enough gravitational pull to grow into galaxies. The first dark matter halos formed, and their gravity pulled ordinary matter into them, creating the conditions for the first stars to form. Dark matter halos merged, drawing their galaxies together, building the galaxy clusters and the vast cosmic web. Every galaxy we see, including our Milky Way, sits within a dark matter halo that is vastly larger and more massive than the visible galaxy. We are embedded in dark matter. We are gravitationally bound to dark matter. our galaxy owes its existence to dark matter. And if the dark Big Bang theory is correct, then in a very real sense, we owe our existence to two Big Bangs. The first created the matter we are made of. The second created the gravitational scaffolding that allowed us to exist. Think about that. You are a child of two cosmic creation events, one visible, one invisible, one that made the atoms in your body, one that made the dark matter halo that held your galaxy together so that your sun could form, your planet could coalesce, and you could be born. Both were necessary. Neither alone was sufficient. If the dark Big Bang happened, then the story of the universe, and the story of your existence, is richer, deeper, and more magnificent than anyone had previously imagined. And we are just at the beginning of this new understanding. The tools are coming online. JWST is continuing to observe, pushing deeper into the early universe with every new survey. The Nancy Grace Roman Space Telescope, expected to launch around 2027, will survey huge areas of the sky at infrared wavelengths, mapping the distribution of dark matter through gravitational lensing with unprecedented precision. The European Space Agency's Euclid mission, launched in 2023, is already gathering data to map the geometry of the dark universe, the distribution of dark matter and the effects of dark energy across cosmic history. The Extremely Large Telescope, ELT, under construction in Chile with a primary mirror 39 meters across, will be the largest optical/infrared telescope ever built when it begins observing in the late 2020s. It will work alongside JWST to study the earliest galaxies and stars in even greater detail. The 30-meter telescope, TMT, and the Giant Magellan Telescope, GMT, are other next-generation ground-based observatories that will complement these efforts. On the gravitational wave front, the SKA will revolutionize pulsar timing, and LISA will open the low-frequency gravitational wave window for the first time. And in particle physics, proposals for the Future Circular Collider, FCC, at CERN, a collider with a circumference of 100 kilometers, dwarfing the 27-kilometer LHC, could search for dark sector particles at energies far beyond current reach. The convergence of these technologies, infrared astronomy, gravitational wave detection, large-scale sky surveys, and particle physics, means that the next decade will be one of the most transformative in the history of science. We are closing in on the nature of dark matter from multiple directions simultaneously. And if the dark Big Bang theory is correct, the evidence will accumulate from multiple independent sources, each reinforcing the others. That is how paradigm shifts happen in science, not from a single dramatic experiment, but from a web of converging evidence that makes the old picture untenable and the new picture irresistible. But even if the dark Big Bang turns out to be wrong, even if a more mundane explanation accounts for all of JWST's surprises, the discoveries of the past few years have already transformed our understanding of the universe in profound ways. We now know that the first galaxies formed earlier and grew faster than we thought. We have evidence for the existence of monster stars, the most massive stars the universe has ever produced. We have identified dark star candidates that, if confirmed, would represent the first detection of dark matter's effects on individual stellar objects. We have found little red dots, a completely new class of cosmic object that we did not even know existed before JWST. We have detected the earliest supernova ever observed. And we have confirmed the most distant galaxy ever seen, pushing our observational frontier to within 280 million years of the Big Bang itself. These are not incremental advances. These are revolutionary discoveries that have fundamentally altered our picture of the early universe, and they were all made possible by a single telescope, a golden eye orbiting the Sun at 1.5 million kilometers from Earth, built by thousands of people over 2 decades, launched on Christmas Day, and working flawlessly ever since. I want to talk about something else now, something deeper, something that goes beyond the specific scientific results and touches on the human dimension of this story. Because science is not just about data and equations, it is about people. People who dream, who wonder, who stay up all night staring at computer screens, who spend decades of their lives pursuing a question that might not have an answer. People like Catherine Fries, who had the audacity to propose that the origin of the universe was not one event but 2. People like Cosmology and Richard Casey, who took that idea and expanded it, mapping out the mathematical landscape of possibility. People like Rohan Naidu, who led the team that confirmed the most distant galaxy ever observed. People like the thousands of engineers who built JWST and sweated through every one of those 344 single points of failure. People like Arno Penzias and Robert Wilson, who discovered the cosmic microwave background by accident while trying to get rid of what they thought was noise. People like Vera Rubin, who discovered the evidence for dark matter and spent much of her career being underestimated because she was a woman in a male-dominated field. People like Edwin Hubble, who showed us that the universe is expanding. People like Albert Einstein, who gave us the mathematical framework to understand it. And people like you, the viewer, who cares enough to spend an hour and a half learning about the deepest mysteries of existence. Every one of these people is part of the story, and the story is still being written. Here is something I find particularly beautiful about the dark Big Bang theory. If it is true, then the universe's origin was not a single, simple event. It was a process, a series of events, each building on the last. The Big Bang created ordinary matter. The dark Big Bang created dark matter. Dark matter's gravity shaped the first structures. Ordinary matter fell into those structures and formed the first stars. The first stars created heavy elements. Those elements formed planets. On one planet, life arose, and that life, eventually, improbably, magnificently, developed the intelligence to look back and figure out what happened. The universe created the conditions for its own understanding. That is not just science, that is poetry. That is the deepest kind of beauty that exists. And consider the implications of the dark sector, the hidden world of dark matter particles, and dark interactions that may exist parallel to our own. If the dark sector is complex, if it has its own particles, its own forces, its own structures, then what else might it contain? Could there be dark atoms made of dark matter particles bound together by dark forces? Could there be dark molecules, dark chemistry, even dark biology? This is wildly speculative, of course, and there is no evidence for any of it. But the dark Big Bang theory opens the door to these possibilities in a way that the standard model does not. If dark matter was created in a separate, complex event, and if it has its own rich set of interactions, then the dark universe could be far more interesting and diverse than we have ever imagined. We might be sharing the cosmos with an entire invisible reality, a shadow universe that overlaps with ours, occupying the same space, exerting its gravitational influence but completely invisible to all of our senses and instruments. It is a humbling thought, and it reminds us that the universe is almost certainly stranger than we can imagine. Let me also address a question that some of you might be asking. Does any of this disprove the Big Bang? Does JWST's evidence for a second Big Bang mean the first one didn't happen? The answer is emphatically no. The evidence for the standard Big Bang, the expanding universe, the cosmic microwave background, and Big Bang nucleosynthesis is as strong as ever. JWST's observations are entirely consistent with the Big Bang. What JWST has shown us is that the Big Bang may not be the complete story. There may be more chapters that we didn't know about. The dark Big Bang, if it happened, would be an addition to the standard Big Bang, not a replacement for it. It would enrich our understanding of cosmic history, not overturn it. This is a crucial distinction. In science, progress usually does not mean throwing everything out and starting over. It means building on what we know, adding new layers of understanding, refining our models to accommodate new data. The theory of general relativity did not replace Newtonian gravity. It extended it to work in extreme conditions. Quantum mechanics did not replace classical physics. It extended it to work at the smallest scales. And the dark Big Bang, if confirmed, would not replace the standard Big Bang. It would extend our cosmic creation story to include a second, hidden chapter. Let me bring it all together now. Let me take you through the full picture, the complete story of the universe as we understand it today, including the dark Big Bang as a possibility, so that you can see how all the pieces fit. 13.8 billion years ago, the universe began with the Big Bang. From a state of unimaginable density and temperature, space and time themselves came into existence. Within the first fraction of a second, the universe underwent cosmic inflation, expanding exponentially and smoothing out any initial irregularities. Quantum fluctuations during inflation were stretched to macroscopic scales, becoming the seeds of all future cosmic structure. After inflation ended, the energy of the inflaton field was converted into a hot, dense plasma of fundamental particles, quarks, leptons, gluons, photons, in a process called reheating. This is when the ordinary matter of the universe was created. Within the first 3 minutes, protons and neutrons fused to form the nuclei of hydrogen and helium. Big Bang nucleosynthesis. The universe continued to expand and cool, remaining a hot, opaque plasma for about 380,000 years, until it cooled enough for neutral atoms to form. At that moment, recombination, the universe became transparent, and the cosmic microwave background was released, carrying an imprint of the early universe that we can still observe today. Now, somewhere in this timeline, perhaps simultaneously with the standard Big Bang, perhaps weeks to months later, perhaps up to a year after, there may have been a second creation event, the dark Big Bang. A separate quantum field underwent a phase transition, releasing enormous energy into the dark sector and creating dark matter. This dark matter immediately began to interact gravitationally with ordinary matter, pulling it together, building the seeds of structure. The dark Big Bang would not have affected the CMB or Big Bang nucleosynthesis, which were already essentially set, but it would have left its own signature. Gravitational waves from the phase transition, rippling outward through space-time.